No. Okay, so hi everyone, thanks for being here. So my pleasure to introduce Chris, who is a professor at UC Davis in California. He graduated from Caltech, then was a postdoc at the National Radio Astronomy Institute Observatory. Yeah. Okay, and the Space Telescope before moving to Davis. And so he works on, he's one of the few real observers in our Lansing collaboration. So we owe him a lot of images that we're analyzing. And so he'll show some work we're doing on that matter with Lansing.
Okay. Thank you, Julia. It's a pleasure to be here in Bologna. Thank you for the invitation. I've really enjoyed my time here. And today I'll be talking to you about a project that's in progress. So I'm not going to show you a lot of results, but I'm going to show you sort of where we're going with this. And so, come on. Okay. So this happened before too. It was working.
You can press the mouse cursor on the.
Okay. All right, so I just wanted to take a step back and motivate this. So as you probably all know, for hundreds and hundreds of years, our science focused on what we now know is only around 5% of the mass energy content of the universe, what we call baryonic or normal matter. And then starting in the 1930s and really advancing in the 1970s, we discovered that there was an additional component in the universe, dark matter, which vastly dominated over the baryonic matter. And then in the 1990s, we discovered something even more confusing, which is that the expansion of the universe was accelerating and we needed a new component in our cosmological model, which we call dark energy. And so today I'm going to focus on this big chunk of the pie. My other work, I do actually look at this via trying to measure the Hubble constant via time delay in gravitationally lensed quasars. But today I'm going to focus on dark matter. And if you've ever seen a dark matter talk, or maybe you've given a dark matter talk, you know that there's an enormous number of possible models for what dark matter is. And essentially, we need more information. And there's a lot of work being done here on the Earth with direct detection experiments. And but astronomy is where we first discovered the need for dark matter. And so I'm going to take an astronomical way of trying to learn about dark matter. Okay, so how can we learn which models are correct? Here is one way of distinguishing between some models, and that is to look at the statistics of low mass dark matter halos in the universe. And our standard model of cosmology, which we call lambda CDM, has dark matter as cold dark matter, CDM, and cold dark matter, it consists of fairly heavy particles, if they're particles, moving non-relativistically. And this model has been very successful in reproducing the large-scale structure of the universe that we see from, say, galaxy surveys. But there may be some tensions between the standard model and the structure that we see on galaxy scales and smaller. And for example, there was this missing satellites problem for a long time, where people knew that when you model the galaxy with cold dark matter, which this picture on the left shows, this is a galaxy, it has thousands and thousands of what we call subhalos, which are low mass dark matter blobs that orbit around through the main halo. And when we looked at satellite galaxies of the Milky Way, we only found a much smaller number. And so this motivated some thought about, could there be alternative matter models of dark matter which reproduced things on the large scale, same as cold dark matter, but would diverge from cold dark matter on small scales and produce fewer clumps. Now, the missing satellite problems may be explained that now that our simulations have gotten more sophisticated, as computers have gotten more powerful, people are now including baryons in the models. And so this may not be a problem anymore, but the door was opened. There are models that have fewer clumps. And so here, for example, I'm comparing a simulation by Mark Lovell. Here he has a halo with cold dark matter. You can see there's many small low mass subhalos. And here is the same halo in a warm dark matter model. And in warm dark matter, you have fewer halos. The particles are moving faster, they're lower mass, and so they can escape from the gravitational potential of very low mass halos. And the result is that you see fewer low mass halos in warm dark matter models. And so here is just a plot of this as a mass function. So on the x-axis, we have the mass of the clumps, and here is the number, and cold dark matter is this black line. And if you add baryons, and this is some work from Julia, I believe. So these are different models with baryons in it, and you can see that it changes a bit the number of low mass halos. But these colored lines down here represent various warm dark matter models. They're predictions, and you can see that as you go to low masses, 10 to the 8th, 10 to the 7th, and so on, at least for some of these models, there's a big difference between cold dark matter and warm dark matter. And so if you can count these clumps and get their statistics, that should allow you to see whether you're down here or up here. Okay, this is very hard. I think I'm going to say that on the next slide, but you can see at this bar here, the halos to the right of this bar, the more massive ones, tend to have stars in them. Their gravitational potential is enough to keep stars that form and gas, whereas the ones to the left are dark. And this shows that there could be a problem. And so this is the problem. It's very hard to detect these low mass halos that we want to see, especially as you go to lower and lower masses. These will be dark. And even in our Milky Way, where maybe we can detect these things with only a few stars in them, it's hard. And once you go to galaxies beyond the Milky Way, if you want to improve your statistics, it gets almost impossible. So we need different ways of finding these low mass halos if you want to take this approach to trying to put constraints on dark matter. And so this is the tool that I use, which is gravitational lensing. And I will try to quickly go through gravitational lensing. Perhaps you've seen enough talks on this, so you know this all already. But here is the basic idea, is that Einstein's theory of general relativity says that space-time is curved by the presence of a massive object, and if light passes through this curved space-time, its path can get changed. And so here we have an example from a textbook that I use when I teach. So here we have a position of the star. The light from the star comes, it passes by the sun, and it gets bent by some angle alpha, and from Earth we would see the star shifted over here. And the amount that the light gets bent depends on the mass of the object and how close it passes to this center, how close the light passes to the center of the mass. The type of lensing that I look at is called strong gravitational lensing. This is a very rare phenomenon, and it's where you have almost perfect alignment between you, the massive object that's bending the light, and the background object. So you can have multiple paths around the object, and you can see multiple images of the object. And that's shown here in this cartoon. So in this case, you would see two images of the background object. And Einstein actually thought about this and realized that we would never see this phenomenon because he was thinking of stars in our galaxy. But Zwicky in the 30s realized that if galaxies were the massive objects that we thought, they have enough mass to separate the images by enough for us to see this. And this, once again, is a consequence of the more massive the object is, the more the light gets bent, which separates the images on the sky and allows us to see them better. Okay, and so here are some examples of real gravitational lenses, if you haven't seen them before. The one on the left is the very first gravitational lens that was found. Once again, Zwicky predicted this in the 1930s, and this lens was found only at the end of the 1970s. So this, I hate to say this as an observer, was a huge triumph for the theorists because they predicted this more than 40 years in advance. Here we have a galaxy that's actually in the cluster. A galaxy cluster is bending the light, producing two images of this quasar. Now we know many more of gravitational lenses. And here are three examples of what we call 4-image lenses. So the typical configurations that you have if you have a point-like object like a quasar is either 2 images or 4 images. And so these are examples of those. And with 4 images also you start seeing an arc, and this is the host galaxy of the quasar that's getting stretched out by the gravitational lens. And here we have an example of something called an Einstein ring, which is when you have essentially perfect alignment between you, the mass, and the background object. So you have many paths that get bent and you see that background galaxy lens into a circle. And these are very, very useful for the type of work that we do. And in fact, this lens is pretty famous in our small community. Okay, so here is just an everyday analogy. If you're seeing gravitational lensing for the first time and you want to talk about it at a party and impress your friends, hopefully you're at a party that involves wine glasses. And you can do this because it turns out that the way that the glass is shaped at the bottom of the stem is a disturbingly good analogy of how light gets bent by a gravitational lens. And so here in this example, the background light source is the candle, and you can see this is a 4-image lens. You can't see the 4th image. This is a 2-image lens, and here we have an Einstein ring. And so this can be very impressive if you're hanging out with the right people, although you may want to make sure that the glass is empty before you start demonstrating this. Okay, so how do we use gravitational lensing to say something about the nature of dark matter? And here is the more traditional technique that we use, and it's called flux ratio analysis. And this is where we use lensed quasar images. So examples where you have 2 or 4 images of the background quasar. In fact, 4 images is much better for this technique. And so I'll talk to you about how this works. So here I have 2, I'm going to start with the picture since I'm an observer. Here we have 2 examples of a 4-image gravitational lens systems where the images of the gravitational lens of the background object are labeled A, B, C, and D. In the top one, you have an E that's actually emission from the lensing galaxy itself. These are radio images. And when we make a mass model of the gravitational lens, so the way that we do this is we see where the images are on the sky, and based on the image configuration, we can learn something about how the mass is distributed in the galaxy that's bending the light. So this is what we call lens mass model. And usually it's pretty straightforward to come up with a very simple analytic model that only has a small number of parameters, and that will match the positions, that will reproduce the positions of the lensed images. So here you would have some lensing galaxy here in the middle, and if you give it the right location and the right ellipticity, you can very easily reproduce the locations of the lensed images. You will also, that lens model will predict how much those how bright those images should be. So the lensing not only shifts the images, but it stretches the images, which causes them to have some magnification. And so your lensing model will predict the image positions and the image fluxes. And so what we tend to see is that for models or for lenses where we have images that are very, very close together on the sky, there are certain mathematical relationships between the fluxes of the lensed images that are close together that are fairly independent of what your choices are for your mass model. And for example, looking at this one down below, if you have 2 images that are right next to each other, they should have essentially the same flux, the same brightness. And here on the top one, if you have 3 images that are very close together, the central image should have a flux that's about equal to the sum of the fluxes of the outer 2. Now, if you have been paying attention and looking at this, you'll see that both of these fail those generic tests. So the one on the top, image B, is actually the faintest of the 3. It should be the brightest. And the one on the bottom, A and B, are not the same flux. They're very different. And in these cases, there has to be something that is acting in addition to this smooth model of the galaxy halo that's causing this difference. And this has to be a small scale feature, some clumpy feature. And so this can be a sign of a dark matter halo that's located in the correct position. And so when we talk about these dark matter halos that can cause the fluxes to change, these can be either within the main halo of the lensing galaxy, so we call these subhalos, or they can be along the line of sight. And when we first started out this business, we were only concentrated on subhalos because that's what we could handle. And then luckily, people like Julia came along that allowed us to incorporate the full line of sight, and we learned actually that the halos between you and the lens system are actually probably in most cases more important than the subhalos in the lensing galaxy. That being said, most people in this small community refer to these as subhalos always, even though even though it's more important than long line of sight. Okay, so there's some other considerations here. I'm showing you radio images here for a reason. It turns out that if you look at these lens systems in the optical or infrared, the emitting region of the quasar has a size scale of about micro arcseconds, and when you have a small scale feature, its flux can be changed by the presence of stars in the lensing galaxy. And there are people who are very excited about this and study dark matter fractions in the lensing galaxy. But for us, the fact that galaxies have stars in them is not so interesting. We want to learn about dark matter. So we need to look at situations where larger masses are changing the fluxes. And to see that, we need to look at things that are emitting on larger angular scales. And that pushes us typically to radio emission. That's the traditional way. So these are both radio images, or say mid-IR emission at 5 microns or more in the rest frame. Or recently, well, starting actually 20 years ago, Ben Metcalf was among the very first people to realize this. If you look at the emission from a quasar, you have the continuum that's coming from the accretion disk of the quasar. You have what's called the broad line region, which is coming from clouds of gas that are orbiting close to the quasar. And they have the narrow line region, which is coming from clouds of gas that are orbiting farther away, that have lower speeds. And the narrow line region, the size of the narrow line region is big enough to avoid this problem of microlensing by stars in the lensing galaxy. And so we have sort of 3 observational routes to studying this: radio, mid-IR, or narrow line regions. Okay, so what we can do, I've shown you 2 examples of galaxies where we do see some kind of perturbations of the fluxes. But what you want to do is look at a sample. This is a statistical method. So you look at a whole bunch of lenses and you see how many of them have flux ratio anomalies. That's what we call this, when the fluxes don't match the prediction. And if you have lots and lots of anomalies, that tells you that there's many, many small halos in the universe, which pushes you towards cold dark matter or colder dark matter models. If you see only a few in a large sample of lenses, that tells you there are not very many small clumps of dark matter in the universe, which pushes you to warmer models. And so this is the idea. And the nice thing about this is non-detections are very, very useful, which sometimes as an observer, not seeing something is not so nice. But in this case, when you don't see this effect, it actually gives you useful information. Okay, so the way we do this is this approach works with essentially any dark matter model that predicts a different number of low mass halos than cold dark matter does. But for various reasons, we've tended to concentrate on warm dark matter models, but we can also look at self-interacting dark matter and fuzzy dark matter, and Julia has been doing this, and see how they change the number as well. So I'm going to, for the rest of this talk, I'm going to be talking in terms of warm dark matter models, but I'm not saying I believe warm dark matter is the correct answer. It's just that it is the most common thing that we compare to when we look at these number of low mass halos. Okay, so when we're talking about warm dark matter, the way that we quantify things is either in terms of what we call the half mode mass, and half mode mass is the mass at which you can just think about it as sort of where the mass function turns away from dark matter. I mean, it's actually done in Fourier space, but in any case, so smaller half mode masses are colder models, because it means that you have to push the lower and lower masses before you see this divergence between cold dark matter and your warm dark matter model. Or we can turn the half mode mass that we determine into a particle mass of the warm dark matter particle, and their colder model should have a larger particle mass, and this is the warm dark matter particle mass. So in any case, I'm going to show you some results from statistics of lenses. So here we have one by Jianwei Shui et al. She was my graduate student, and another one contemporaneously by Daniel Gilman et al. And the really nice thing about these analyses is they both use samples that were about the same size, but the data sets were completely independent, the models were completely independent, and they ended up getting essentially the same answer. So they put some upper limit on the half mode mass, which translates into a lower limit of the particle mass. Their upper limit was around 10 to the 7.8, and which translates into roughly, okay, I should have written this down, but I think it was roughly around 5 keV for the particle mass. And then much more recently, just this year, there was a paper using JWST. So JWST gives you the emission from the dust torus in these lens quasar systems that give tighter constraints because it's a bigger sample. And here is this example from the Keeley et al. Result. This is showing the half mode mass. Here is their upper limit on what the half mode mass could be, which is, so it needs to be less than 10 to the 7.6, which translates into a warm dark matter particle mass of around 6 keV. All right, so this seems great. I've spent a lot of time working on this. I've had graduate students work on this, but it turns out that there's a problem that we ignored for a while. Well, we weren't even thinking about this for a while, and then we started incorporating it, and then this leads to some problems. So the issue that we have with this flux ratio approach is multipoles in the lensing galaxy. And so when we make our mass models, I told you we can come up with fairly simple mass models that will reproduce the lens positions, the image positions very well. And typically these are elliptically symmetric mass distributions where the density is described as a power law that falls in the center. And these work fantastically to reproduce the image positions. However, we're getting more sophisticated as time goes on. We look at what we see in nearby elliptical galaxies, and when you look at isophotes in nearby elliptical galaxies, they're not perfectly elliptically symmetric. A lot of them show some deviations from this pure elliptical symmetry, and these are often described in terms of boxy or disky isophotes. People quantify these isophote shaped additional components with multipoles, and here's just one way of quantifying this. So you have some amplitude and a cosine term and another amplitude and a sine term. And there's a nice paper by Howe et al. Who looked at a whole lot of galaxies from the Sloan Digital Sky Survey and looked at the distribution of third and fourth order multipoles in these isophotes and found, that they were centered around 0, but there was lots that had some multipole components. And so we said, why not stick this into the mass? Because the light is not perfectly elliptically symmetric. Why not consider the mass being deviating a little bit from elliptical symmetry? And when we did this, we found an interesting result. And so here's the basic idea. There's a lot of writing on this, but I'll try to explain it. We made some fake lenses. And what we did is we generated these lenses by using describing the mass distribution in the lensing galaxy as an elliptical power law, no multipoles. And we added in cold dark matter halos, both in the lensing galaxy and along the line of sight. We did this many, many, many times. And for each of our fake lenses, we said, okay, what's the most extreme flux ratio changes that we see from the perturbing halos, the cold dark matter halos? Okay, then we said, all right, we know now we have a lens system that has some flux ratios. Let's try to fit this with just an elliptical power law plus multipoles, no halos at all. Can we do that? The answer, yes. And for almost for all the things that we did. And that's what this top plot shows. It may be a little hard to see, but in each of these plots, there's a gray band that represents the observed flux ratio. The blue histogram in each case represents the flux ratios that you would get out from a whole bunch of elliptical power law models with no multipoles. So it's just a very simple elliptical power law. And you can see that the blue does not match the gray in many of these setups. So these would be in the way that we talk about this, these would all be flux ratio anomaly systems. But if you add in multipoles, you get the red distributions, and the red distributions shift right to the observed. And when we look at this, we see that the amplitudes of the multipoles that we're finding are very reasonable compared to the Howe et al. multipoles that we see in the isophotes of nearby elliptical galaxies. So, and that's what this plot, you probably can't even see it, but this plot here, we have some red contours that represent our prior, which is taking the Hal multipoles and we expand them, the priors a little bit, and the black is the multipoles that were found. So in every case, the lens modeling, if we give it the fluxes and multipoles, it is easily able to find a multipole solution that reproduces the fluxes, but without requiring any crazy multipole term. The values, the amplitudes of the multipoles are very reasonable. So our conclusion from this is that based on the data alone, which is just 4 image positions and 4 fluxes, you cannot distinguish between multipoles or halos. Okay, we see this as a big problem. And you know, I've talked to some people who have knowledge of this, and their answer is, yeah, but you know, halos are much more common than multipoles, so you know, it should be halos. But that is a prior. That is not what the data are telling you. And so our conclusion is that you need to be very, very careful when this approach that you're not dominated by your prior, and we don't really understand a way to get away from being dominated by your prior. So if you're trying to say, is you know, dark matter cold or not, and your prior is where there should be lots of halos, that biases you in one direction. Okay, so what do we do now? Well, sorry, I jumped ahead of myself. Okay, so just to say some things about the flux ratio approach, it's great because it can detect very low mass halos down to 10 to the 6 solar masses, and JWST gives us great insight into it. But it is purely statistical. You don't ever directly locate where the perturber is that's changing the fluxes. And this is the big one. If you really are properly considering multipoles, you may actually be getting very, very little information out. And so what we're doing in the short term is we're actually going to see what happens if we try to do a dark matter inference from real lens quasar systems, but including multipoles, and see how much of a change it makes. We also, because we said, okay, we see multipoles in isophotes, we stick in multipoles in the mass that are roughly of the same order, and we see this effect, but we really want to look at simulations and see, do you actually see multipoles of this level in galaxy structure? We don't know. Okay, so hopefully this is something that will happen over the next year or two, and we'll find something out there. What do we do in the meantime? We look at a different technique for detecting low mass halos, and this is something called gravitational imaging. So I'm back here to my example, but here we have the Einstein ring analogy. And imagine if and in fact, this may even be true in this case, if there's imperfections in the glass, small scale imperfections in the glass, you don't see a perfect circle. You see a circle where it wiggles a little bit as you go around the circle. And so this is the idea behind gravitational imaging. So you essentially have a double lensing phenomenon. Here I show a beautiful example of a group scale lens known as the clone. So in this case, we have a small galaxy group, which is, you can see these 3 yellow galaxies in the center. They're the central galaxies of this galaxy group, and they're lensing a background blue galaxy. And you see this beautiful long arc and the counter arc. And if you're paying attention, you see that there's something interesting going on here. And if you just look at the arc, just the blue emission here, you can see it comes down, there's a gap, some appears here, and curves around, and then it continues on its way. And that tells you that there's some mass there that's disturbing the arc. And of course, you say, clearly there's mass there. We see this yellow thing right in the middle. And that is a small galaxy that's part of the group. So this is not, you know, a huge ask to believe this. But the idea is that we would have known exactly the location and mass of that little galaxy, even if there was no light coming from it, because all the lensing cares about is the mass and the mass distribution. It does not care about the light in the lensing galaxy. And so here we have another way of detecting low mass halos. Now, this is a fairly high mass halo. It's around 10 to the 10 solar mass, because the main lensing thing is a galaxy group, probably 10 to the 13 solar masses. And so we want to push this to smaller scales, where we have a galaxy in the middle, and the thing that may be perturbing this is a subhalo or a line of sight halo. Now, you don't need to see actually this full ring with your eye. We have our modeling analysis can detect even smaller effects. But we need to do this, and we need to get very high resolution, because remember, the angular resolution, well, the separation that you have caused by the lensing depends on the mass of the lensing. So as we go to lower and lower masses, the separation becomes smaller and smaller and smaller, which means you need better and better angular resolution to see it. Okay. So here are some examples of gravitational lensing working. This was the first one. So Simona Vegetti discovered this in what's called the jackpot lens. So here we have the lens emission. And when she did her analysis, she detected something here. So this bottom right panel shows you what's called the convergence correction. You can think about it as a sort of a density map. And so you need some clump of mass right there to reproduce what you see. So this gave her a substructure of about 4 times 10 to the 9th solar masses. You can do this with ALMA data. So this was Yasser Hezeva did this, detected something about 4 times 10 to the 8th. This is better angular resolution with ALMA. There's a high angular resolution setup. And then this is one from Keck Adaptive Optics Imaging. And Simona also led this paper. And here we see a little density enhancement at the top. That is robust. We also had HST data of the same system, and all the data sets required a potential correction right here. So we detected this. And this was a halo, if it was at the redshift, if it's a subhalo of the lensing galaxy, which it may not be, it has a mass of 2 times 10 to the 8th, and this is a galaxy at redshift 0.9. So we're detecting small things at high redshift, which is pretty neat. Okay. So what about multipoles? I just went on and on about how they mess things up for the flux ratios. It turns out that they also can affect this gravitational imaging technique, but what it tends to do, it reduces the region in which you're sensitive. So here we see, okay, let me try to describe maybe this one on the top. So you see the black contours represent where the light is in this mock lens. The purple areas show you where you could detect a perturb or a small halo of a given mass. And if you add multipoles, what it tends to do is it shrinks the area down to the ring. But and this is work done by Connor O'Riordan, who's a postdoc at MPA, and Simona Vegetti. And so what they found is on the ring and near the ring, things are fine. You don't have to worry about the multipoles, but away from the rings, you're no longer sensitive. And so, and that probably is because with this lens emission, you have more constraints on the gravitational potential of the lensing galaxy, rather than just 4 image positions and fluxes. So what this means is essentially because we're reducing the area that we can probe, we need larger samples, but multipoles do not kill this method. Like I would argue they kill the flux ratio method. Okay, so here we see high resolution imaging. I'll talk, and I said this already, so I'm just going to not really say much about the slide. Once again, lower masses mean smaller mini rings, which means you need higher angular resolution. And the way we get this is either we put a $1 billion telescope into space, so you can use the Hubble Space Telescope or the James Webb Space Telescope, or if you're clever, you can do this from the ground if your technology works. And here I have examples of the Keck Adaptive Optics system. And the idea here is you correct for the blurring effect of the atmosphere. And if your correction works well, then you're observing with a telescope that's 10 meters across rather than 2.5 or 6.5 like HST and JWST. And bigger telescopes give you better angular resolution. And so here is my favorite lens for describing this. And of course, this is not the typical one. It's the best case for describing this. So anyway, this is what it looks like from Keck with no adaptive optics. This is what it looks like with Hubble Space Telescope. This is a very red lens, so you only start to detect it in the infrared bands. And here's what it looks like with Keck Adaptive Optics. The scale bar here is half an arc second, just to give you a sense for if there's any observers in the room. This is really impressive. But you can see the difference between the Hubble Space Telescope and Keck Adaptive Optics. It does make a difference if your mirror is 4 times bigger across for your angular resolution, as long as you can correct for the atmosphere. Okay, so with Keck, even now we can push down to subhalo masses of around 10 to the 8th, which pushes us into the dark sector. So we start to get into an interesting area, and we're trying to improve the adaptive optics system on Keck to push it a little bit farther to the left, which gives you even more difference between what warm dark matter models probe and cold dark matter. Okay, so we want to push down the mass function, and how do we do this? Well, one way of pushing to lower and lower masses is to get better signal to noise ratio observations of your arc. That's not crazy. The higher sensitivity you have in the arc, the better you can see small deviations in the arc. Angular resolution, I've argued for this before. So you want to push to the highest angular resolution you can get. And then this last one is not so obvious. It turns out that it actually depends whether the background object that's being lensed has a smooth light distribution or a clumpy light distribution. It's much easier to see bright clumps shifting by a little bit than to see a smooth distribution that's slightly distorted. So Julia did a nice paper where she actually quantified a lot of this. But here you can just see, so here we have a clumpy distribution, here we have a smoother distribution. And once again, these bright knots, if they shift a little bit, it becomes very obvious in your residual map. Okay, number 2, let's choose lens systems that optimize our chances for measuring possible perturbers, because our constraints depend on essentially how many perturbers we expect to see from a given sample. So, okay, you want a big sample. Okay, that's number 2 here. And you want lenses that are informative. So, the non-detections, if you have a lot of them, that actually tells you something if you have a bigger sample than a smaller sample. But another way of sort of increasing your expected number is to look at galaxies that have number 1, good mass sensitivity, which I just talked about. Number 2, long arcs. If you have a really long arc in the sky, there's many chances for a halo to be sitting near that arc and deflecting it. And then the last one, high redshift. As I mentioned, when we first started this, we were just concerned with subhalos in the main galaxy, but there's lots of halos along the line of sight, and Julia showed in another paper that, in fact, this may be the dominant signal. And so the longer the line of sight is to the lens of galaxy and to the background source, the more chances there are that a perturber will end up in the right place to cause some deflection in the ring, and the higher our expectation value is. Okay, so this is what we can do. So here we have, okay, this is just from this paper. I'll just say, we said this already. Okay, so this will get us to the program that, this collaboration that Julie and I are part of, which we call SHARP, which stands for the Strong Lensing at High Angular Resolution Program. I like it because we want sharp images. So that's part of the, motivation for this thing. And it's not we're not capitalizing weird letters in the middle of words either. Okay, so we look at originally, so galaxy lenses with long arcs and 4-image lens system. And we do this, well, the way it started out was with adaptive optics with CAC. And this is actually some pictures that I've taken while I'm observing. So this is the Keck laser system going up, creating a fake star that we can use to correct for the turbulence in the atmosphere. And this is actually my observations are causing the laser to be fired, which is kind of fun. Okay, so why AO? I've sort of said this before. You can get better angular resolution with Keck plus AO than with HST. Here we have the same lens I showed you before. Here we have another lens, the one that you've seen before. And in each case, the last column is the Keck AO, and the previous columns are HST. These are both very red objects, so if the wavelengths are comparable, the resolutions, you really win with Keck. For our typical observations, we get full width half maximum of their point spread function around 60 to 90 milliarc seconds. So 0.06 to 0.09 arc seconds. And for me, as a professor at University of California, it's much easier to get observing time on Keck than it is on the Hubble Space Telescope. And here I just want to show you, if I look at this lens, we look at the HST data analysis and the data analysis using the AO. Here are parameters of the lens model. What they are is not important, but what you can see is that the blue, which is from this HST image, gives you much bigger posterior distributions on your parameter values than the red. Having that higher angular resolution really allows you to say something important about the mass distribution. Okay, so even with the laser, you need a bright star that's relatively close by. It's more of a challenge than you would think because it needs to be within about an arc minute of your target. And since we're looking at extragalactic targets, or we're looking out of the galactic plane, it's sometimes hard to find a bright star. We need a bright infrared arc. because the AO system works best in the infrared. And the problem with pushing to the infrared is that the light distributions in the galaxies are smoother, so we don't get that really clumpy, nice clumpy message, light distribution in the background source. Okay, a possible problem, and this is one that people often bring up, is the point spread function of adaptive optics. It's a little bit crazy. It may not be as big a problem as we think. So here's just an example of each row is the same star. It's a bunch of different individual exposures of the star that were taken. And what you can see is that there is some noticeable change in the point spread function with time. But this may not be as much of a problem as you think. It turns out that the AO point spread function sort of looks like this Prussian hat. So we have what's called the diffraction limited core. That's the very high resolution. And then we have this broader base that is the atmospheric seeing, which is typically of the order of an arc second or so. So you have a 60 to 90 milliarc second spike on top of the broader base. And what we see when we look at these is that that diffraction limited core is actually pretty constant. It's the base that's moving around and doing crazy stuff. And it turns out that what these arcs tend to be sensitive to is that diffraction limited core. So it may not be as much of a problem as we think. Okay, so very quickly, this is our initial sample of lenses to try to do gravitational imaging with sharp. And these were selected by just lenses that were known at the time. This started about 10 years ago, and lenses where we can find nearby bright stars. And there was a lot of work to find the tip tilt stars that we need to have close to this. And so we have a nice sample. They look beautiful, but the Einstein radii are pretty small. So this scale bar in each case is 1 arc second. So we don't have really long arcs on the sky. And just sort of by chance, a lot of them tend to be somewhat lower redshift, which is not ideal. But now we have entered this era of big data. We have these huge sky surveys. So there's some that have happened already. And then, of course, Euclid, which I hear great things about, but I know nothing about because I'm an American and not a European. And Rubin. And so we should have like thousands of new lenses to look at. Already, we're starting to see lots more. People have developed really cool machine learning tools for finding gravitational lenses in these huge data sets. And so the number of potential lenses is really going up. And then because we have Gaia, we can cross-correlate and find tip tilt stars automatically, which really speeds things up. And this has allowed us to create a second sample in the big data era where we pick and choose galaxies that lens systems that are more useful to us. So looking at higher redshift systems, looking at systems that have longer arcs. And so just to demonstrate that, here are the Sharp phase 1 systems and the Sharp phase 2 systems where the fields of view are the same in each case. And you can see that the arc lengths tend to be much longer in the phase 2. And this is the redshift distribution. Blue is Sharp phase 1 and orange is Sharp phase 2. So we have higher, sort of longer lines of sight, longer arcs. And so anyway, we have 2 very nice systems. Julia and Cristiana Spingola are working hard on the gravitational lensing analysis of phase 1. And my grad student Prayag, who's sitting there in the back, is starting work on phase 2. But we've had huge numbers of problems with the KEC AO system, which is getting old. We've had problems with weather. And so these data are not quite deep enough. The sensitivity is not fantastic on them. So nice things about gravitational imaging. We directly locate the perturber position and its mass. There's many more lensed arc systems than there are lensed quasars, so we have bigger samples to choose from, and we're much less sensitive to problems caused by multipoles. But with our optical IR observations, we only really push down to about 10 to the 8th or a little bit better, which is not, we want to go to lower masses. And every lens system needs to be modeled in detail, so we need to find some way of speeding that up. So what can we do for the future? One is improve the KEC AO system. And this is something that's happening right now. It's called Kappa, the KEC All Sky, something. I don't remember what that is. Precision adaptive optics. There we go. This should help us. And improving the adaptive optics system pulls more of the light into that spike in the center and takes less of the light out or more of the light out of the base, which is to improve our signal to noise ratio. And then also, if we can push adaptive optics into the optical wavelengths, that gives us better angular resolution because your angular resolution goes as the wavelength divided by the diameter of the telescope. New facilities, you know all about Euclid. It's going to be fantastic. LSST will also give us great images. And then eventually we'll have extremely large telescopes to follow things up with, which gives us much better angular resolution and much better sensitivity. So here is a simulated version of this lens with the ELT that Simona created. And then also something we started to work on right now is VLBI observations of lenses, where you have these very, very thin arcs and angular resolutions of just a few milliarcseconds, super high angular resolution. Simulations show that you can see by eye a 10 to the 7th solar mass, the effects of a 10 to the 7th solar mass blob, and you can detect, say, 10 to the 6th or smaller blob. This is fantastic. There's only a few systems that have this lensing configuration with radio, but it's great. So final thoughts. Okay, we need, for AO, because that's what I focus on, we need systems that have arcs that are bright in the near IR, which causes maybe some problems for lens search algorithms, although maybe not with Euclid. Long arcs are often, long arcs come with bigger mass systems, which may be galaxy groups. So we don't know if there's a weird selection effect. How do we speed up the modeling? This is always the thing that's slow. For gravitational imaging, you need detailed models, which take a long time. So we need to speed that up somehow. Okay, I just showed you some great VLBI. Why are we still doing this? Well, we still have many, many more things with near IR rings. And so right now it's still reasonable, and we can combine our AO and VLBI imaging. So in the past, when people have tried to use gravitational imaging to say something about dark matter, these are constraints on the warm dark matter mass, where going higher up is a tighter constraint. And these two orange points here are the previous gravitational imaging analyses by Simona and one of her former students, Elisa Ritondale. And they do not look good on this metric, but the first one had a very low redshift system. The second was too shallow. So I really think that with our sharp adaptive optics, gravitational imaging, we should be able to push these points up here and actually make it competitive and exciting for the future. All right, thank you very much for your patience. And